Hello. As part of the Micro and Smart Systems course, today we are going to study yet another modeling topic, which is torsion and twist. We know that elastic structures deform in many different ways. One that we have studied, the simplest case, is axial stretching, and then we have studied bending. Today we are going to study or discuss torsion. First, let us discuss what torsion is. All of us know, if not torsion the word, but twisting is something that we all are familiar with. Twisting is you take something, it can be a stick or a piece of string or a wire or a plate, a shell, anything that you take, you apply a certain motion which makes it deform in a way that is different from bending that we have studied. So, let us look at that. Let us take the kind of structures that we have already studied. Let us say I take something that looks like this. Let us say it is fixed into the wall on the left side. This side it is fixed into the wall, and this other side is free. Okay. When I apply a load in this direction, all it will do is deform in the axial direction. So, this for us is axial direction. So, if I apply a force in this direction, it is going to stretch, that we have already discussed. Now, if I apply a force in this direction, which we call transverse direction, transverse load or transverse direction. So, this is axial direction or axial load. If you apply there, it is going to stretch, or if it is other direction, it will contract. If it is this way or if it is this way, okay, if I put x, y, z here, if this is x, this is y, this is z. Okay. X y plane is x axis this way, which I let us say this is x axis, axial direction, and the y or z axis, if I apply forces, this is going to bend. So, this is one way of deformation, which is axial deformation. Okay, if this is x axis, that is axial deformation, and if it is loading about the y axis or z axis, in those directions we have bending. This beam like structure is going to bend. Now, we also have to look at the moments. If there were to be a moment about, let us say, the z axis, okay, so this is the force in the x axis, bending will be caused by force in the y axis or force in the z axis, and if there were to be a moment which is whose effect is to turn something, if there is a moment here, let us say that is about the z axis, we have studied that moment as well, whose effect is also bending, and if there were to be a moment about the y axis, that is this is our y axis, if there were to be a moment about that, the beam will bend into the plane or out of the plane. So, moment about y axis also will cause bending. That leaves one more thing, we covered fx, fy, fz, and moment about y axis and z axis. What if there is moment about x axis, that is like that? Okay. The effect of that is to twist the beam, that is the twisting, and this loading we call is torsion or torque. Okay. Torque causes torsion or twist. Okay. So, this is familiar to all of us that if we take a shaft, okay, something like this, it is a beam basically, and if we fix one end and apply a moment, that moment about this x axis, this is what we are calling it x axis here, up is y axis and going that way perpendicular to the axis of the beam in this way is z. If there were to be a moment about x axis, that is called a torque. We use capital T to denote the torque. Okay. Now, the effect of this is to twist it. How much does it twist? So, if I take something and hold one end fixed and twist the other end, how much does it twist and what kind of stress does it create in this beam, which we normally, because shafts are the ones that hold this torque load, we usually call it a shaft, but it is a beam. It does not need to be only of circular cross section, it can be any cross section, I can twist them. So, I can have an I beam cross section which we see in civil engineering structures, but some of the microstructures also have this. I can have something like this, a beam, what we call an I beam, because it has I type of section here. Okay. So, when you have this is a section, this also can twist. Sometimes whenever there is a building collapse or something, if you go and see, look at the beams, you will see them bent and twisted in different shapes, and that twisting is bending and bending are very common features of deformation of elastic bodies in general. There is one more thing that we should not get confused at this time, where what we use is called a torsion spring. Okay. This torsion spring is actually a bending spring in the sense that if there were to be a pin joint and we have a rigid body going, rigid body is something where we neglect the deformation. If I connect something like a coil spring, if we have that coil spring, that spring actually does bend, it does not twist. Twist is something like this, we take something and then apply a torque on it. To see this, if this is a beam, bending is apply the load this way or that way, I apply force that way or this way, that causes bending, but if I or movement about the this axis or that axis, if I apply movement about this axis this way, that is torque, right. If I take something that is very flexible such as a straw, then I do this, you can actually see it twist, and that is what we are talking about. Whereas, this coil spring that we are talking about here, which is simply a spring that is wound in the form of a coil like this, I am just exaggerating it. So, if I have a pin joint here and attach something here, one end attached to this, other end attached to a fixed frame. Now, as I rotate this, this is going to bend, and that also going to provide a torque about this axis. So, people call it a torsion spring, but that torsion is not torsion, actually it is bending. Okay. Having understood what torsion is, let us see where we find it in microsystems. In fact, we find it in many places and microsystems is not an exception. Let us say we take the suspension that is shown over here. This is a suspension, if you recall, for a gyroscope, or it is a suspension for a 2-axis accelerometer. So, this proof mass, the center, what we have shown here, this one can move in the horizontal direction and the vertical direction, that is, this is horizontal direction and this is a vertical direction, or you can call it x and y, with equal stiffness. It is a symmetric structure, it has that. But what if there were to be a movement like a tilting of the piece over which this 2-axis accelerometer is placed, and there can be a movement or twisting about, let us say, this axis. What if there is a torque applied on this. Then these beams that you see, that is this beam and this beam and this beam will start twisting, or if there is a movement about this axis here, then the beams which are vertical here, they also starts twisting. So, we need to account for when there is a torque here, they will twist, when there is torque here, these other beams also will twist. So, we have to see the effect of torsion on these, so that we can see whether the proof mass and the capacitance at these beams will change or not. Okay. Similarly, here these other beams also, depending on where the torque is applied on this central platform, these also can experience twisting. So, whenever we have the axis this way, if there is torque T acting, that will cause this body whose axis is this to twist. Okay. So, when apply torque this way, we have to see which beams will experience, because the beams that are horizontal like this, they will experience twisting. When it is here, their axis aligns like this, they will start twisting. Okay. So, in these cases we probably do not want the beams to twist, but they will. So, we have to account for those unintended effects to be taken into account in the design, so that any of these other motions would not affect our accelerometer. But there are also a few devices which need this twisting or torque, and we look at one example over here. So, this is Texas Instruments, this is a product from Texas Instruments company, who have done extensive research on this Microsystems device, which is an array of micro mirrors, which are shown here with the leg of an ant to compare how small these mirrors are. You can see a little bit of close up of view here, and then just one mirror is shown here. Okay. And if we look at the model of this, which is colored for clarity, we can, and also blown into pieces. So, here is the central portion. We have the yellow structure and then the red ones, which are called here torsion hinge, because that they make this H shaped structure to tilt this way or that way, and that is done because these torsion hinges can twist, and the force application is done through these electrodes which are underneath, which will exert an electrostatic force to tilt this H shaped one this way or that way. In other words, this H shaped structure will twist about this one to make this one move this way or that way, and there is a mirror attached, and the mirror will tilt this way or that way to shine the light beams in different directions as desired in this array of micro mirrors, which is used for projecting images, such as what we connect to the laptop. Some of the laptop projector systems have this array of micro mirrors. So, this is what we are talking about. Here is a beam, the red colored one. If I were to just write it, draw it here. Okay. This is the red color system. Now, we have a torque on it. Again, know that the axis of this red colored beam has a rectangular cross section, and there will be a torque load, because if I apply a load here, there will be movement about this axis, which we call torque, and that torsion of this is what makes these mirrors tilt one way or the other. So, there are a number of examples in microsystems where torsion is important. Let us take a closer look of this Texas Instruments mirror. So, this is where the torsion happening. Okay. We want to model that, and you can see the real structure, scanning electron micrograph supplied by Texas Instruments, where these micro mirrors are there. Underneath that you can see the electrodes, and these are the critical portions as far as the mechanical behavior is concerned, and that is a crucial part. These mirrors undergo many millions of cycles, probably even billions in their lifetime, because if they are being used in the projector systems, they have to twist many number of times. Okay. Let us discuss this with the simplest case, which is the torsion of a shaft. So, shaft, as I said, is just a rod of circular cross section and it is fixed at one end and free at the other. Does not need to be free to apply torque or torsion, but we just take a simple case where we have one end free, other end is fixed, and now we apply a torque that is shown here. This is torque T. Okay. Then what happens to it? Then imagine that this end is fixed, that is completely fixed, this is completely free. In between, if you take something, if I take this disc that is shown, so this disc should have the same size as this one. So, we just take, I have taken it inside of certain radius r rather than taking the, this is small r, whereas the radius of the big one is capital R, that is this diameter of this one is 2r, but I have taken a disc that is only a little bit and then see what happens to it. So, you can imagine that when I take this one and try to twist it, the whole thing is going to twist. It will be 0 twist here at the fixed end, and at the free end it is going to have the maximum twist. That is, if you imagine a straw and do it, you will see that one end that you are holding fixed is not going to twist much, other free end will twist a lot. Now, if you take the disc somewhere in between and look at what is happening to that thing. So, here we have taken the disc, the same disc that we have shown here. Okay. This disc we have blown up to a large size to see what happens. If I take some of these letters have moved, let us not worry about it. So, we will redraw them. So, I am going to take this piece, a very small piece on that the disc. This is A, this is B, this is C, and this is D. Okay. Now, this is the center of that circle. So, when it twists, A will move to another point. Okay. Let us say A has moved to A prime and D has moved to D prime, and B and C we assume they are fixed because we want to see the relative deflection. So, relative deflection means relative twist. So, let us say the left end of this disc I keep it fixed or imagine it to be fixed, relative to that at a distance dx, how much does it twist. So, I have taken on the periphery of this, let us draw it for clarity again. If I take the disc, okay, I assume that this is fixed, so that I can talk about relative deflection. So, now if I have a rectangle here, we take it to be very small. So, we take an angle so that this portion can be approximated to a rectangle. So, here we have A, B, C and D, this is the center. When this what was there here, now A goes to A prime somewhere here, D goes to D prime. Since these are fixed, we will leave them as it is, and now we will see what happens to A, B, C, D. It actually becomes A prime, B, C and D prime. Okay. So, the effect of torsion is actually to cause what we call shear in this rectangle that we have taken. To see that, here we have shown in the dotted line. Okay. So, I have taken a square as shown here. Now, I have made this point move here, move point here, just like what has happened here. Okay. So, if I say this is my A, B, C and D over here, this has moved to A prime, that is this point, this has moved to D prime. So, this has been turned this way, that is I have applied a force here to make it shear, and that is what happens to torsion, because when this surface rotates relative to the other one, it actually causes a shear. That is something that we had not discussed at length before, but we did talk about normal stress and normal strain a lot. In normal stress, normal strain, you have a force applied normal to the surface that changes the volume of the body. If there is a stress here, it will go this way. If there were to be a stress here, it will go that way, right. Original one has become this rectangle. If there were to be a stress there, this can become a rectangle like that. That we talked about normal stress. The shear stress is different from it. Here we apply force parallel to the surface. Here it is perpendicular or normal, here it is parallel. So, that causes what we call shear strain. So, we have shear stress which is denoted by tau and shear strain which is denoted by gamma. How are these related? There is a property, material property called shear modulus. This is similar to what we had Young's modulus, which relates normal stress with normal strain, and that relationship we had called Hooke's law. Similarly, this is a Hooke's law for shear. If there is a shear stress, there is a shear strain, we have a modulus which we call shear modulus, because its effect is to shear parallel to the plane, and that is related to Y, Young's modulus, and nu, Poisson's ratio. Poisson's ratio is something that we have already discussed in one of the previous lectures. This Poisson's ratio and this Young's modulus give the shear modulus. Sometimes this is also called rigidity modulus. Rigidity modulus. So, having defined Hooke's law, now we go back to see how we can define strain here, which is shear strain. If we go back to the previous slide, we said this rectangle that we have shown is going to shear to other triangle which we have shown here, okay, and this angle is our shear strain according to the way it is defined. So, that is what we show here. If I look at that BC, okay, that is this length from here to here will be still equal to this length. So, if I say the BC here is equal to AD, which is also equal to A prime D prime, and if you look at this figure BC that we have, and if we say this length of it from here to here, it is going to be the same, which we can write gamma times dx and r times d phi, because we have taken the length of this. If you notice, we have taken that to be dx, okay. This is r, how much it has moved, okay. This is this little distance, that r times d phi, because what was here has turned by that angle, or this has turned by this angle. That small angle is d phi. R times d phi is equal to gamma, the shear strain, times dx. So, we have this here. So, gamma times dx is equal to r times d phi, okay, and we will replace this gamma with tau by g from here, okay. Tau divided by gamma is equal to tau divided by g is equal to gamma. So, gamma we replace by tau by g into dx equal to r d phi, or we can write tau is equal to g into d phi by dx into r, which is what we have written here. Shear stress is equal to shear modulus times rate of twist. This is the quantity, rate of twist of the shaft along the x axis, along the axis, times the radius at different radii. Remember that we have taken this disc of radius r, which is less than the capital R. At any point we will be able to know what the shear stress is, provided we know what this is. We know G, and at any point R we would like to find the shear stress, we have to know what that is. Okay. How do we find that? Here you notice that we introduce two things, we introduce the shear stress tau and then shear strain. We know one quantity that relates both of them, but that is a Hooke's law, but in order to determine statics we need Hooke's law and we also need equation equilibrium. So, that is what we will next go to in order to find this rate of twist along the axis of the shaft, and that leads us to the equilibrium equation, which is if I take that torque multiply by area of cross section, I get a force that is acting parallel to it. So, I have this shaft surface and I have shear stress everywhere, I am multiplying by the shear stress with the area and then integrate over the entire area by taking moment. So, I take a point at the center and I look at all the area and try to do that. So, let us sketch that. If I have a cross section area like that, this is the center, I take a small piece here, okay, that has an area, let us say dA, we multiply that with the shear stress, stress is the force per unit area, that will be the force which is acting parallel to that surface, okay, and then I multiply that force with that radius where it is located and then integrate over the entire area of this circle. Okay. So, we take a piece anywhere and try to fill it, that is what integration means, to get the total torque due to the force. This is the dF that acts parallel to that surface, we integrate over the entire thing, and when we do that we substitute for tau which we just derived, G times d phi by dx times r, and then we have dA now and then r. When you integrate, you notice that we make an assumption here that d phi by dx does not change on this area of cross section. So, when you take area of cross section everywhere it is the same, that is an assumption that is valid for circular cross sections, because all the twisting happens in the same place by the same amount, it does not change within the area of cross section. That is not true for other cross sections, as we will mention later. And G of course being a property of material, that can be taken out of integration, because that also does not change on this area dA over which you are doing integration. Now, this quantity which is integral of r square dA done over the entire area is denoted with a letter J, which is called polar moment of inertia of the area of cross section. Okay. That is the J. Okay. That, as you can see, is defined as integral r square dA done over the entire area of cross section. So, we have derived T, because if I take this force and take the moment about this axis, if I take moment about this axis, right, what I get will be the torque that I am applying, which we discussed earlier today, the torque. So, the torque is equal to this total thing, that is equal to Gj times d phi by dx, okay, where we assume that d phi by dx does not change over the cross sectional area. Another thing we also say is that this d phi by dx can simply be put as phi times L. If you are interested in the total torque somewhere, d phi by dx, if you say that is constant from the fixed end to the free end of the shaft, we can say if phi is the total twist at the free end, then you can say that is phi, that is over a length L, instead of dx we put L, that becomes our twist and torque relationship. We had Hooke's law to relate shear stress and shear strain. Now, we have got a relationship by using static equilibrium, something relates torque with the twist, okay, that is T Gj by L, and this we can say is torsional stiffness, torsional stiffness, just like we had a bending stiffness, axial stiffness, now we have torsional stiffness. This is the torque which have a unit of Newton meter, and twist will have radians or degrees, and then torsional stiffness will have Newton meter per radian. Okay. So, we have that T over phi, and phi as we just called is the twist of the shaft. Okay. And now, at any r if we want, we go back to the relationship we had, T equal to G times d phi by dx. Instead of d phi by dx, we have put phi by L, okay, which we had discussed over here, what we have done. Then we can say T by J R, because now you look at this relationship between T and phi. So, we can get shear stress as T divided by J times R. Now, these three quantities, that is phi by L times G, we can write T by J from here, phi by L T divided by G J over here. So, if I take that relationship, I get T by J R. This is how I can get the shear stress. When R equal to 0, there is 0 shear stress, that is clear. When I am twisting it, this point will not experience any shear. The point that is away will get a twisted little bit and so forth. When I go to the edge, then this will be the largest. In other words, if I take any line here, it will have 0 shear stress, it will be maximum, it will go like this. When R equal to 0, that will have 0 shear stress, and R equal to capital R, okay, this is our capital R from here to here, that will have the maximum shear stress. That is how shear stress varies here. Okay. Now, what happens when you have non-circular shafts? Let us say I have, like the TI mirror, if I have a rectangular beam which they called torsion hinge, let us say I fix it over here, and about this axis I apply a torque. Okay. Can we apply that formula that we just derived? Actually, we cannot, because some of the assumption that we have made here, that d phi by dx is constant over the area, and also it is the same, or it is linear as a function of x, that is d phi by dx. If we just put it as phi by L, the twist is 0 at the fixed end, that is here, and then it maximum at the end, that will not also be valid for other cross sections, because if you imagine this rectangular box or rectangular beam, if we take it and twist it, it will warp. Okay. So, we have to define something called a warping function, and here this warping, because this is rectangle, that will remain like this. Let us say this gets rotated, because that is the effect of twisting. If it becomes, let us say, at an angle from here to here, the whole thing, because what was here now let us say has gone here. So, it has warped like this, this has gone to the other side, and so forth, everything has turned. Okay. So, that the way it has gone. So, this warping is rather difficult to imagine, but if you can imagine that, whatever assumptions we made earlier for circular cross sections will not be valid here. For this, there are approximations where we can define a J equivalent, okay, that is a polar moment of inertia equivalent, and still use the formulae we have derived for twist of the circular shaft. This J equivalent will be given in handbooks for different non-circular cross sections. If you look at any strength of materials books, handbooks or textbooks, you can find J equivalent for different cross sections, and that is what we need to use if you want to analyze the Texas Instrument torsion micromirror. Now, let us look at an application of this torsion for something that is very simple and what we are familiar with. If we take any ballpoint pen, all of them have a spring in it, such as the one shown here, which you call a helical spring. If it is a compression spring, you apply a force, it is going to decrease in length. What happens? How do we analyze? It turns out that the kind of stress that this torsional the helical spring experience is actually torsion. So, that diagram is shown here. If I cut somewhere like I have shown, if I just cut the spring over here, I would see that there is a force here. Since it is upwards over here, there should be a downward force on the cross section for equilibrium, okay. And if I take moment about that point, that we call torque. This torque is actually moment about the axis coming out of the screen. This is the torque, okay. Likewise, if I cut anywhere on this, anywhere, we only see torsion and there is a force parallel. So, if I were to take this rectangle cross section and blow it up, okay, there is one force that is acting over here, that is parallel. So, that is called the shear, and also there is a torque about an axis perpendicular to the cross section area, that also causes shear. So, this is a case of a structure that is deforming where there is shear due to this vertical shear force, a concept we had discussed in the context of bending of the beams, and also we have the torque now which also causes shear, and that shear effect is what we need to take in order to analyze this. If you are surprised that something where you have taken a coil spring and you are just compressing it and that is causing a torsion like effect, let us take a piece of string that is shown here. So, I just hold one end and start twisting the other end. So, I am holding this end fixed and start twisting this other end, okay. So, do it as many times as you wish, the more you do it the better will be the effect, and after that just like this helical spring, just bring these two ends together and what you see is that it twists, right. If I undo it and let us say all this torsion is gone, if I take this and bring it closer, it is just bending, nothing is happening to it. The moment I take this, okay, keep it taut and do this twisting, that you can see what I am doing, just turning, that is the torque, that is twisting, and after that when I bring, it just becomes this. So, here this torsion spring that we are talking about is actually undergoing this torsion effect, and that is why it is coiled, and when you do it, it gets more coiled and the torsion we see. And DNA in our bodies also has this kind of a feature where there is a helix that turns around what are called histones, and that makes it collapse into a loop such as the one that you just saw with this piece of string. Let us analyze this using what we have just discussed. First, the torque that we have seen. So, we saw that there was this cross section and there was a force F here and there was a torque, and that torque is F times the diameter of the helical spring divided by 2. So, if the d here is this the quantity, okay. See, diameter of the coil of the helical spring is d, half of that because we have to take moment about this, right. So, this force acting here F times d by 2, that is the radius of this one, half the thing here, that will be the torque acting on this section, okay. And now we will use this occasion to discuss the application of Castigliano's theorem, which we had discussed in one of the earlier classes. Castigliano's theorem, which says that due to this torque, if I want to know what the twist is, we have derived the formula just now, but if I have to look at this entire spring for a particular force that is applied on this, if I want to know how much it is going to compress, let us say I keep this end fixed, apply a force, this will move down here. If I want to know this deflection, we will write the strain energy of this whole spring and take the derivative of. So, if I want to find that delta of this spring, I will take partial derivative of the strain energy of this spring with respect to the force. This is Castigliano's second theorem, if you remember from one of the earlier lectures, that deflection delta is simply partial derivative of the strain energy with respect to F. So, we have to write strain energy of this structure of the entire spring, strain energy of the spring, okay. let us do that. So, first we have here this torque equal to F d by 2 and the strain energy, which is the area under the torque and the twist diagram. That is, if I were to plot the torque here and twist here, the area under this is the strain energy, just as for a spring half kx square, half kx is the force, x is displacement. So, we have torque here multiplied by F, they will have units of energy, that is the strain energy, and we substitute here for torque what we had just derived, that was phi L by G j. If we go back in what we have just discussed, the torque here is equal to phi G j by L. So, if we substitute that over here, then we will get this strain energy equal to T square L by G j. Okay. That gives us the strain energy, and the T here is F d by 2. Then we have we can substitute for T F d, and also the L here is n times pi d. How does that come about? Pi d is, if I take each turn of this spring here, this is pi d, one coil, and I have n turns like that in a coil. That is the total length of this. If you go back to the string experiment, I want to take the entire length of the spring. If I take this spring and uncoil it, I will get a shaft of length L equal to number of turns times the periphery of each of the loops, okay, length of each loop of the thing. So, n here is number of turns in the spring, and we can substitute for L over here, and we need to know the G for circular cross section, okay, the J, sorry, the polar moment of circular cross section is given by pi wire diameter of the spring. The spring, there is a wire, and wire is wound in the form of a coil to make the spring, that is d to the 4 divided by 32. Substitute all of that, we get a strain energy which is shown over here. Let us write it a little bit bigger. The strain energy turns out to be 4n, substituting all of these, F square capital D coil diameter cube divided by G and d raised to the 4. Okay. So, we have this total strain energy. If we take partial with respect to F, then we focus on this, the 2 will become 4 and 2 8, okay, that delta that we wanted, which is dou S E by dou F, turns out to be 8 n F d cube by G d to the 4th. Okay, that is a deflection. So, how do we define spring constant K? F divided by this delta, which will give us G. F goes, this is F here, F divided by delta this way, it will go G d to the 4 divided by 8 n d cube. That is the spring constant. We have used this concept of spring constant many times when we discuss the lumped modeling of the suspensions of microsystems, and if we have a real spring such as the one shown here, we can get its spring constant in terms of its parameters as shown over here, where we have used Castigliano's theorem and the fact that the compression of a helical spring is equivalent to twisting its wire, as we just saw the string experiment, and that spring constant we have derived. And if we also take into account the shear over this area because of the force F, if you write the strain energy due to that also and again use Castigliano's theorem, you will get an additional component which will give this K. In addition to this, there will be another term, a correction term if you will, that will be given by, so there will be a correction term here which is 1 plus capital D square by 2 small d square reciprocal of that 1 over that. That will be the effect. 1 plus this is going to be correction. Whenever we have this d by d ratio beyond certain point, only then this correction factor becomes important, otherwise it is not going to be an important contribution to the spring constant. So, that comes because of the vertical shear force due to the force F. We have illustrated the effect of torsion and twist in microsystems, and also did a generic example of a helical compression spring that we see all around us, including our ballpoint pen. We have derived an expression and revisiting Castigliano's theorem to apply it and find a formula. Now, we have also introduced as process a concept of shear stress. We had talked about normal stress quite a lot, but today we introduced the concept of shear stress, whose effect is only to change the shape of a body to shear it, where there is a force parallel to the surface, as opposed to normal stress where the force normal to the surface. Having discussed all of that, today we can make an attempt to consider a general state of stress. Instead of thinking about 3-dimensional bodies, let us look at only 2-dimensional bodies. A microsystem gripper is shown here. When I apply force here and here, this portion will move. If there is an object here, a biological cell for example, it can apply force on it. Today, a number of people are looking at making these micro machined grippers, where you can hold a single biological cell such as a red blood cell, white blood cell, or any number of cells that are there. We can hold them and test their mechanical properties, understand the role of mechanical behavior or response in the assessment of the biological state of a cell. So, when you look at those devices, let us say we have a macro version of that, a large scale version of that is shown. When I apply a force over here, let us change the color of the ink. If we apply a force over here, this portion is going to move. As you can see, this gap that you see has reduced to a small one by applying force. How do we analyze this? What happens any of these structures? If I take an element over here, okay, an element of such a structure, what will be the state of stress? I have taken a small segment. Just imagine a point where there is a small square. What kind of stress will be there? There will be a normal stress, okay, in the x direction as well as y direction. There will be a sigma x here, and there will be a sigma x plus a little bit more, because stress, if you assume that it is not constant, which is true for a structure like this, we have taken a small one. At one side if it is sigma x, other side you say that there is a little bit of variation, which we say d sigma by dx times delta x, where we say the size of this square is delta x that way, and similarly the size of this in that direction is say delta y, okay. That will be the stress on this side, and let us say if I say this is sigma y, and this will be sigma y plus d sigma y by dx times delta x. In addition to this, two normal stresses is what we have shown. There will also be a shear stress, a shear stress that will act on it like this and also like this. That we denote by tau xy. Tau xy means that it acts, the force acts in the x direction, that is this direction, and it happens to be on this surface whose normal is given by the y axis. We have tau xy, the same tau xy here. So, that is a state of general stress, a general state of stress acting in 2 dimensions. Okay. So, if I take another structure, another micromechanical structure, where there is some force over here, and it is going to make this platform move this way or that way, depending on force direction is this way or the other way. And if I take a small particle like this, there will be sigma x and little bit more than sigma x plus d sigma x by dx delta x, and then there will be sigma y, as we just said, sigma y plus d sigma y by dx delta x, and there will be tau xy over here and at this corner on this sides. The other side we have moved in the x direction, y direction, that will be d tau xy by dx delta x, that one, as well as this will be tau xy plus d tau x by dy times delta y, that is this one. Okay. If you take all that and do the force balance, because these are stresses, we can multiply by area. So, sigma x I multiply by area, and the other side I multiply sigma x plus this by area, and if I sum the force in the x direction and y direction and do the moment, okay, then I get the equations which become our equations of equilibrium, which we have taken this element. Okay. And one more thing is that what if there is an element on a boundary, that becomes this will have external torque, external force, not torque, applied on it, and this side will have sigma x, will have sigma y, and will have tau xy. Okay. For both of those, that is interior element and the boundary element, if we sum up all these forces, that is as we just said, d sigma x by area of that, area of this sigma x is acting over this over here, this height is dy, and if we assume unit thickness into the thickness of this sheet or a 2-dimensional structures, that becomes dA. So, force times stress is equal to force, this is the area times stress is equal to force. Similarly, stress times area is equal to force in the x direction. If we sum up all that, if we also assume that there is a body force, this B of x is body force. Body force is like gravity or centrifugal force and forces like that, which act at every point inside the body, that is why it is called body force. That will be, if we say force per unit area or unit volume, we take dx dy and unit thickness, that gives us the Bx. If we do that, we get an equation of motion for the x axis. Similarly, if you do that for the y axis, you get that. When you do for the wedge element, so you take the force sigma x here, sigma x times dy times 1 unit thickness, that is a force due to that, and there is also a shear stress which is acting over dx times 1, that is dx for us, that is this, that is acting this way, that is also minus here, and then this external force that is acting, which we denoted by T, will have component Tx, that is shown here, that acts over a surface ds, that is what we indicated, this is dx. With Pythagoras theorem, that will be square root of dx square plus dy square, and if you introduce this direction cosines nx and y, nx is the cosine of the angle between the x axis and this ds, that is normal to the surface over there, and this is the cosine of the angle between y axis and normal to the, this is the normal to the wedge at that surface point. Okay. If you do that, you get this third equation, which is the boundary condition. Similarly, if you do the same thing for the y axis, you will get for the boundary another one. If you put together all of them, we get the equations of static equilibrium for general state of stress. These are equations of static equilibrium in 2 dimensions. Okay. You note that these two we got by writing the force balance in the x and y directions for an element which is interior, and these are the force balance equation we wrote for an element that is on the boundary, like a wedge element. This for the interior, this for the boundary. These are the equations that we solve in order to analyze a structure such as this, or a structure such as this, or structure such as this. Any structure you imagine, we can solve them, but of course we have to use numerical methods such as finite element analysis or boundary element method for solving these things, whereas the bars, beams and twisting of the shafts we can do analytically by writing down formula. And let us also discuss, now that we have discussed static equilibrium that came from the balancing of the forces, let us see the other concept which we have always said we need only two things when it comes to statics of elastic bodies. One is static equilibrium balancing of forces and the other is Hooke's law. What is the equivalent of Hooke's law for the general state of stress? So, for that we also need to define strains that we have already visited. We have the strain for the x axis and y axis which are normal strain, and there are also a shear strain where an element such as this gets sheared to that one, then we say these angles are the shear. Let us draw it properly. If I have that, let us say I hold this fixed and apply a force as we have done today. If this point moves here, this point moves here, okay, this angle and this angle are the shear strain. Now, we have divided into this portion and this portion. So, we can actually write the definitions of these strains here. So, epsilon x, that is a normal strain in the x axis, is given by dou u by dou x, and normal strain in the y axis is dou v by dou y. U is the displacement in the x axis, v the displacement in the y axis. Then the shear strain, which you denote by gamma x y, or some people write as epsilon x y also, that is given by dou u by dou y plus dou v by dou x and half of that. See that this is dou u by dou x, here it is dou u by dou y, here it is dou v by dou y, here it is dou v by dou x, half of it, that shear strain. And what relates this stress and strain, the Hooke's law, we had already seen this in the context of defining Poisson's ratio, and today we have defined this Hooke's law for shear. When we put these things together, we get a relationship where there is general state of stress in 2D, general state of strain, that is normal stress, normal stress, normal strain, normal strain, shear stress, shear strain. This becomes the equivalent of Young's modulus. There is Young's modulus y and Poisson's ratio nu for an isotropic material, and similarly we can do it for the 3 dimensions also. But of course, the equations of equilibrium that we just saw over here, these have to be solved numerically. So, we have to go for numerical solution when the geometry is complex. For that, finite element analysis is absolutely necessary. Let us just capture the main points of what we have discussed today. We have discussed torsion and twist of circular shafts and introduced the concept of shear stress and shear modulus, and we said people use an approximation for non-circular shafts, and we also did an example to derive the spring concept of helical spring using the concepts of torsion that we have learnt, and we also finally discussed the general state of stress for 2-dimensional bodies. If you have any questions, you can send me an email at suresh@mekinch.iise.ernet.in. Thank you.